All right. Hi, you guys. We are going to be doing sections 5.1 and 5.4 in two different videos using the same foldable here. Section 5.1 introduces the absolute value function, and we look at the coefficient a in the absolute value function and what it does to that function. 5.4 will be the bottom half of the foldable, or the bottom 2/3 of the foldable, h and k, and how that transforms an absolute value function. So let's go ahead and annotate that this is going to be for section 5.4 down here for h and k. And today we're going to focus on a, which is related to section 5.1. Okay, up here at the top, we've got our formula for an absolute value function, which is f of x equals a times the absolute value of x minus h plus k. In your parent function, you have just the f of x, the function of x, equals the absolute value of x. This is called the parent function, which we have defined in our vocabulary. And it's basically the absolute value function without any transformations done to it. We are going to look at what changing a does to this function. In the parent function, the value of a is just 1, right? We could identify this invisible 1 here. That would be multiplied by the absolute value of x. When we change that number, it does some things to our absolute value function shape. Remember that that shape is in the shape of a V, right? It looks something like this on a graph, and it has symmetry, meaning it's a mirror image on either side of a line. When we do something to this value a and we change it so that it's not 1, we're going to see that we can compress, stretch, and or reflect the parent function. Okay. Another thing we're going to want to note out here outside of our note taker before we look at an example is that the vertex of an absolute value function, which is the highest point or the lowest point, depending on the way the V shape, the direction the V faces, right? So in this picture that I drew, the V is facing up, so the vertex is the lowest point. But the V shape could also be upside down, in which case the vertex would be the highest point. So it's the minimum or the maximum of the function. The vertex is always h, k. So let's write that over here. The vertex in an absolute value function is always h, k. And that's important to know because when we're making a graph, we want to put this in the middle of our table of values that we would use to make a graph. And that's because an absolute value function is symmetrical around the vertex. So if you have the vertex in the middle, you're going to have some x values to the left and some to the right, and you're going to be able to see both sides of that V shape. Okay, so that's an important tip for graphing. So if we open this up, I'm given an absolute value function where that value of a is no longer 1, right? It's now -1/2. Sometimes I like to write the formula for an absolute value function above or below my function just so I can see the values of a, h, and k more easily. So this says g of x equals a times the absolute value of x minus h plus k. So now I can see that a is equal to -1/2 and h is equal to 0 and k is equal to 0 because there's no value subtracted from x inside the absolute value bars, and there's no value added to the absolute value expression on the outside either. So I can see that that could be replaced with 0 and 0. So h equals 0 and k equals 0. And since I know my vertex is h comma k, my vertex is going to be 0 comma 0. Okay. Now I'm going to go ahead and graph this next, and then we'll talk about the question down below where it says what is the transformation. So to make this graph, I need to make a table of values. So I have some points to put on my graph. This is where that tip that says put your vertex in the middle of your table comes into play. So graphing 5 points is a good solid number for absolute value functions, so I have 5 columns in my table. My vertex that I know is going to be on this graph is 0, 0. So I'm putting that in the middle. Then I'm going to pick values below 0 and above 0. So I'll just do -1, -2, 1, and 2. You could have also done like -2, -4, because my graph goes all the way up to -5, right? But doesn't matter. Now I'm going to plug in these numbers into my absolute value function and see what the y values are, okay? Now I know it says g of x, it's function notation, right? But when we plug in our x values, our output are our y values on a graph. So, for example, if I were to plug into -2, this would say y equals -1/2 times the absolute value of -2. So y equals -1/2. The absolute value of -2 is +2, right? The absolute value is always positive because it's a distance. And -1/2 times +2 equals -1. So when x is -2, y is -1. And I can do that again with -1. So y equals, I'll use a different color, -1/2 times the absolute value of -1, which is -1/2 times 1, which is -1/2. And over here, y equals -1/2 times the absolute value of +1, which is -1/2 times +1, which is also -1/2. And this should always happen, right? If it's the same distance for x, it should be the same for y around the vertex because it's a symmetrical shape. Okay, and then lastly, y equals negative 1/2 times the absolute value of positive 2, which is negative 1/2 times positive 2, which is negative 1. Once again, it matches. Okay, so you're going to get to the point where you don't need to show all of this, but I am just showing you how I'm getting those values that I'm going to graph now. Okay, so coming over here, I have my points that I can plot. So negative 2 comma negative 1. Negative 1 comma negative 1/2. 0, 0. Positive 1 comma negative 1/2. And positive 2 comma negative 1. You'll know you're on the right track if your graph is forming a V shape, right? I could even figure out what these extra values are by plugging those in. Like I know if I plug in negative 4, and I do this in my head real quick, the absolute value of negative 4 is positive 4, and then negative 1/2 times positive 4 is negative 2. So that's going to end up being here. And it's going to be symmetrical on the other side with positive 4. And then I'm going to connect my points to make my V shape. Okay, so now I want to compare this shape to the parent function, which if you look back in your vocab, when you graph the parent function, it's just a regular V shape that faces upwards, and the slope of that is up 1 over 1, right? Up 1 over 1. So this shape, compared to that, is upside down. So the graph is, instead of saying upside down, we say is reflected over the x-axis, right? So if our parent function looked like this, I'll just graph it as a dotted line. So it'd be like this, the absolute value of x, right? So the absolute value of 1, is 1. The absolute value of 2 is 2. The absolute value of negative 1 is 1. Absolute value of negative 2 is 2. So this is my parent function. Compared to that, the graph is reflected over the x-axis. And it's also wider, right? Because when I go down 1, I'm not going over 1. When I go down 1, I'm going over 2. Okay, that's making the V shape spread out more. It's making it wider. So the way that we say this is that it's vertically compressed, right? Imagine pushing down vertically on the top and the bottom of this V. It would flatten it out and make it wider. So it is vertically compressed by a factor of 1/2. And this is the vocab that you're going to be expected to use when you're solving these problems. So we're always thinking about the compression or stretching as a vertical motion. So when the graph is wider, as in the parent function, it's vertically compressed. But if you have a situation where the graph is narrower, it's vertically stretched. Okay, imagine pulling it from both ends. The A value tells us some things. Before we even graph it, we can tell what's going to happen to the graph. Okay, If the A value is a negative, the graph is going to be reflected. When the absolute value of A is less than 1, so let's think about this. A is equal to negative 1/2. The absolute value of A, or the absolute value of negative 1/2, is positive 1/2. Is that less than 1? Yes. When the absolute value of A is less than 1, the graph is compressed. Right? Because this slope, we can kind of think about the A value like the slope of the line. In the parent function, the slope is just 1. A is equal to 1, so you're going up 1 over 1. In this example, the slope is kind of like 1/2. You're going down 1 over 2, down 1 over 2, right? And when a slope is less than the original, it's not as steep, right? It's flatter. So this is where we're going to have a wider V shape, and it's going to be compressed. Whereas if the absolute value of A was greater than 1, for example, if this was like a 3, when you graph it, you would notice that you'd go up 3 over 1, up 3 over 1, and the V shape would be skinnier. It would be narrower. And when that happens, it is stretched by the factor of A. Okay, so these are our key points of information for our absolute value functions. Before I end, one more thing that you might be asked to identify is the axis of symmetry for an absolute value function. In other words, the line that cuts the V shape in half. And if you're asked that, you want to write your answer as an equation. So remember, we write the equation of a vertical line as x equals a number. The number that x is going to equal is whatever the x value of the vertex is, which in this case is the variable h. Okay, that's the x coordinate of the vertex. We'll look at this a little bit more closely when we actually look at the transformation that h does in our next video, but just in case you're asked, the axis of symmetry you would write as x equals a number. So in this example, the axis of symmetry, the line that cuts the shape in half, is x equals 0, right? This y-axis, x equals 0 is the vertical line that cuts this shape in half. That would be the axis of symmetry.